virus. They are not showing symptoms of the virus, while the 20% of them are the ones that are showing symptoms. So we have it as SIA for why this is symptomatic infected. We also have recovery compartment for human compartment, because people can, these asymptomatic people can also recover without knowing it too. Then of course the people that is symptomatic can recover by treatment, by going to the hospital. Then these asymptomatic infected is also can die of the disease. The symptomatic infected can also die of the virus. But symptomatic infected, we do not consider that there are no symptoms of sickness in them. Now, if you look at this human compartment, we did not consider recruitment, a birth rate, and death rate, because we are trying to study within 6 months of the virus, within the peak of the virus in Nigeria. So we look at the very short time situation. Now, we have this red arrows has to do with the shedding. We take it that shedding can be the symptomatic and symptomatic infected can be shedding the virus in the environment, where they represent the environment. The environment can be known in the environment, whether in hospital setting or in-house. Now, we also have the rat population, which also we consider, because we consider the death rate and death rate. Rats produce almost every time. So within the 6 months, you can have a lot of upstream. So we consider that. And those also we do not consider death rate. We say that rat does not die, so we need to produce. Then we so we have the rats also face this virus in the environment. So that's what this virus is. So we have our system of occupation here. With this, now this the flow diagram generates the system of occupation we are using to that. So from our OG, this is our cause of infection. Our cause of infection has to do with it. This beta has to be human to human transmission. The human can come in contact with that. Then, although it's in a very rare case, it can be not as common when it has to do with the environment. We also have the human to rat to human transmission rates, because we think that some settings in Africa, like some places in Africa, there is a bushmeat, so someone can come in contact with that in the process of catching up the bushmeat, so someone can get infected. They also have a virus to human that's coming in contact with the environment, and the case can be characteristic of that. For the same thing goes with cause of infection for the rats. We have rats, which can be taken by upstream. Then we have the environment too. So these are our initial condition of that. We have the total population of human, which is given as the total population of the. So we have our initial conditions because it's going to be infection. So these are what the description of other parameters in the work represents, and the values that we use for our solutions. So we now, then before we stop that, we'll try to transform the model into another model system, because we want to look at prevalence of the virus in the environment. So we do that, to carry out that to produce this particular system of population we have. So these are our SI, the total population now is equal to 1. So every the state variables here, SH, SI, IH, they are all population now. So this is what we have to use that. And this is what each of these new transform parameter represents. This new transform parameter represents, we have it in our initial conditions. So what we do is that we try to look at, okay, that first system of information we have, we will consider one environment. We have to carry out a analysis on that, trying to look at the partial rank correlation coefficients of each environment. So this is the magnitude. We look at the peak of the magnitude of each of these infected populations. So infected population, for human population, we add both the symptomatic and symptomatic together. Then we have the rat population, the infected, and we have the environment, which is V. Now, if you look at what we have here, We can see for us to have a significant parameter, we look at the PRCC that is greater than or equals to 5, 0.5. So from what we have here, we notice that the rat, this is the death rate to the rats, rodents, the rats. Then this is recovery rate of the asymptomatic infected. And this is the transmission rate to rats. And this is transmission rate to human to environment. So we notice that these 4 parameters here, that rat population, as rat parameters are very significant in the transmission of this particular virus. Now, when we come to the rat population, we see that the death rate and the transmission rate rat to rat is also very significant in the transmission of this virus, because when it's negative, what it means that when it's a negative PRCC, it means that increasing that function will reduce the population, while reducing that population, that particular parameter will increase that particular population. But when it's a positive, what it means that increasing it will correspond to increasing the population that is under study. Now, when we come to environment, the magnitude of the peak of environment, we see that the rats, this is a transmission, rat-to-rat transmission, and this is the death rate of the rats. Then also see this is the shading of the virus in the environment by the rat, and this is also the birth rates of the rat. Then this is the decay rate of the virus in the environment. Now, when we see all these things, we notice that the rat parameters play a very important role in the transmission of this disease. Now, the same thing goes to the peak of time. Peak time, what contributes to the peak time? Because why do we say peak time? Because if you know the peak time, what contributes to the peak time? Actually, reduce it in order to stretch the peak. Then it will now reduce the peak, the magnitude of the peak, but it can stretch the time in which the outbreak will reduce. And that means many people will not get infected, but it will only stretch the time. So that is what we consider the peak time. Then when we also look at this, we notice also that the rat parameter also play an important role in this transmission. So the question we ask ourselves, can we actually control the rat parameters in the Lassa fever transmission? Although studies have said that when you reduce the death rate of the rat rates, you are going to reduce the virus in the environment. When you reduce the birth rates of the rats, you are going to, but you know how tricky rats can be. We cannot control the population of rats, especially rats are produced more during the rainy season. So what happened there is that we now focus on, we now fix all the rat parameter constant and focus on other parameter to see what we can do, because since we cannot control that. And if you also want to say, okay, they are going to use some of the rat poison or whatsoever, they also have their own implications, which can also be very dangerous to the system. So that's what we want to, okay, when I fix this parameter, what happened? What other parameter plays an important role in the magnitude and the time too. So this is when the rats demographics are hold constant, so that we can see what other parameters play an important role. So from what we have here, we'll see that for the human population, recovery rate of the asymptomatic infected is very important. And in the real sense of it is very, very important, because since the asymptomatic infected people are not aware of their disease, so now, if they recover fast, it will actually reduce the virus in the environment. But the question is, how can we identify those people? So this is what we're also trying to look at this study too, how it can be implemented in real life. Then also look at shedding rate of the rats is also very important, and which can also actually control. One of the ways we can control that is that instead of spreading food outside, trying to dry them, we can actually find a way that is safer for us to dry these foodstuffs in order rats not to get in contact with them. We can also try to storing our food in the house in a closed container where the rats cannot get in touch with them. So the same thing. So when we come to environment, you see that decay rates, the virus decay rate is also very important, and the shedding rate is also very important. Because if the rat is not shedding, because we say that the human is also shedding it, but in the hospital base. So we see that the shedding rate of the rat is very, very important for us to control that. Then we also look at the rat population too. what plays out in that. I think this may be a mix-up in the VRR. So the same thing goes with the time. When it comes to the peak time, there is none of the parameters is significant for the rat and the virus. We notice that it's only in the human population that parameters are very significant. And one of them is the shedding rate of the rats in the environment, and the transmission of human to the environment is also very important in order to control that. So from what we have here, this is what we consider one environment. But we say that our aim is to consider where we have a true environment. Which of these environments is more? Is it outside? Is it within, inside the house? So we also try to modify the model to have something that looks like this. The only thing that happens different from what we have before, because we have divided the environment in two ways. The V, it has to do with inside house environment, while the W has to do with the outside house environment. So this outside house environment has to do with everything that has to do with outside. So we want to see how those two environments play part in our transmission of the disease. That's Africa. So we have our model as like before. Also though we have our source of infection too, as we agreed like before. The only thing that added is that we have this outside environment. We have divided our environment into two. So this is our reduced transmission. We transform our system to what we have here, like before. Same thing goes with this. So we'll come up with our analysis. So from what we have in our analysis, we also carry out the same analysis we carried out before. But in this case, we included our outside environment, and the V has to do with the inside environment. So we see that is almost very similar with what we had before. But what we have here is that both environments are playing a part in the transmission of disease. But we notice that transmission outside is much more significant than transmission inside the house. Then also, we also look at when it comes to the environment, the magnitude of the virus for the V, each of their decay rates play part in each of their environments. So this is what we have for the transmission. Then also notice that the both recovery rates of both infected people are also very significant in this study too, which is also something we have to consider. But of importance is asymptomatic infected. Then we also have the transmission to both environments to be also significant. So this is what, for the magnitude, this is what we have. But in this study, in this particular simulation, all the rat transmission are held constant. So only consider the other parameters. So the same thing goes with it. We have that for the peak time, we have that the rats, the infected rats, the both environment, none of the parameter is significant. The significance has to do with the human population. In the research of it, when there is always an outbreak of the virus, we always about the human population. So we see that both transmission rates, the transmission rates to both environments are very important. Now, the transmission rate of the rat to human and human to human is not significant. But we say that.
Joanne, do try and be fast because we have less than 5 minutes.
Wow. So this is the magnitude. Then this is the peak of the time. So this is what is ongoing work. I'm still working on it to represent what is really happening. And also from the work, we can also implement the data we have from what we have from here. So in conclusion, what we have is that at least we have looked at the transmission dynamics of Lassa fever in one environment and two environments. And from what we have, we can see that decay rates, rodent shedding rates, and the transmission rate for human to both environments are very significant for the peak time of infected humans. So that means that for us to control the virus in the environment, we have to do that. What are the controls we are going to implement to increase the decay rate of the virus in the environment, and also to stop the shedding of this virus by rodents in the environment, also to stop humans getting in contact with the contaminated environment. These are the things that we have to implement this control to see how it can help stop this problem. So that is my presentation on my work. So thank you for your attention. But I have something to talk about, just a little shaded to talk about in the career perspective and experience as an African young researcher. I feel that from my own experience, I feel that Although there's nothing I'm going to say that is different from what I've been hearing, because we are having a lot of challenges for us to meet up with what is happening in the world there. For example, you have a conference to attend and your institution says they cannot sponsor you if there is no money. And they expect you to have papers, have a conference attendance in your promotion. So how will that one be? These are one of the challenges that you get from when you want to expand and network with other people. And it's very difficult for you to even to sponsor yourself for a trip. You have to save like 6 months salary for you to go to a trip that is outside your own country. So that is one of the most times also affects, especially the young researchers like me. We find it most times because it's when we go out there, we network with people, we have information. It will also boost your research, because one thing I find out during the COVID was one of the times that I had a breakthrough in my career, because that is when I saw the power of networking and collaboration. As someone that is in research, I've never, that was a very big, especially the UK APACY. I just want to use this opportunity to thank UK APACY organizer. I really appreciate that program. The program was like an elevator to my career. It exposed me to so many people, so many collaboration I have. I cannot take them for granted in my life. They have been opened up for me and to my students. I just want to say thank you to UK APACY for organizing that program. Also looking forward to such program for my graduate students.
Thank you.
I just want to say, I just want to appreciate Professor Jane Harapana, who happened to be my host in York University, for hosting me in the university. I want to also appreciate AAUW. AAUW is the American Association of University Women, which I got a 1-year postdoc sponsorship to visit York University. I just want to acknowledge them and thank them. Also acknowledge York University, Toronto, Canada, for giving me opportunity to be in their institution. Thank you very much.
Thank you very much, Wedu, for the wonderful presentation. It's really exciting, and at least you have tried to show some applications or contribution in solving a real-life problem, which focus on the Lassa fever. And of course, it's one of the virus that is really affecting the society, especially in Nigeria. Thank you very much for that. So I don't know if anyone has a question or observation. Please, you can unmute your mic and make the question or the observation.
Okay, thank you, Chimando, for your presentation. It was quite interesting.
Thank you.
Yeah, I wanted to ask, it means that climate change plays a major role since we're looking at the environment.
Yeah.
So what's your take on that aspect of climate change?
For the climate change, it plays a major role in the transmission of Lassa. But I say that what we are considering first is I want to look at the environment that contributes more. Then we can now look at the climate change, because there is already work out there in climate change impact on the Lassa. But in that, those work are considered only human population and rodent population. So what we are trying to look at in this work is that where we look at different, where environment play the part. So after then we cannot consider the climate change.
Okay.
There is a work in progress. I'm also open for research collaboration.
Okay.
Because I have some data, I don't know how to go about it, so I'm open.
Yeah, it's okay. It's interesting. And for the Lassa, because you say you have the data for 3 years data coverage. So I don't know what is the coverage? What is the coverage of the data? Do you cover the whole country or maybe some specific area? And is it on daily basis or monthly, or what aspect of data?
It's weekly basis and is for the country, but most times, most of the reports are from where is mostly endemic. But by SCDC, the data is from SCDC website. They keep updating Lassa cases every week.
Okay. SDCC or what?
NCDC, Nigeria Center for Disease
Okay.
Control.
Okay. NCDC. Okay. So it's important. It's interesting. We wish you all the best. Thank you for the presentation once again, and we look forward to meet you for future collaboration. Or you have, is there anyone have question?
Yes, I wanted to make a quick comment.
Okay.
Yeah, it's a question as well. So yeah, I know NCDC in Nigeria is the organization that collects, and they also have the right to disseminate data on infectious disease and so on. So, but oftentimes when you go on their website, you don't really find any up-to-date information. So I'm quite surprised to hear that you can get up-to-date data on Lassa fever from their website.
Okay,
So,
they have, what happened there is that the one I have is from 2019 to 2021. When you go to their website about Lassa, so you have to take a paper and pin down every week what every week they report it. They are reporting it, they are updating it every week. I think that period I was following it up, I think every week I get a new report. You know, when there is a Lassa, you know, one thing with the Lassa virus, when there is outbreak of Lassa virus, when there is a reported case of Lassa virus, you know, the particular person is no longer under your care. Even the hospital will call them immediately to take a sample. So and when there is death too, they take over because they feel that the corpse may also be very, very infectious. So that is why, because I had this family friend doctor that, so that is why I got this information. They're always involved. They call them immediately. They're always involved. So if you want, I can also check the website.
I know. So you basically extracted the data from maybe
you extract data. Yes, you have to extract
from the situation reports, right? Yeah. Okay, I get that bit. The other question I have is this. This work is super interesting, I've got to say. I think one thing that people are interested in this kind of work is, you know, when you are able to analyze the data with this sort of analysis you've done, are you able to sort of predict maybe future numbers of cases of the disease, or maybe kind of predict areas where outbreaks are likely to occur in the future, you know, so that effective maybe intervention strategies can be developed and implemented in those areas. So can you answer such questions, you know, with this kind of analysis that you've done? Yeah, thank you.
Okay, like I said, like this is like we try to, the parameters we use here, we have not fit the data to our model. So this is what we are also in the process to do. We just want to see how, if we are from the work that I've done so far, which parameter plays a part, then after then we can fit our data to it. So, and I'm also talking about areas in Nigeria where that this can be, you know, because we are not studying a particular area, we are studying in the whole, you understand? So may not really give, it's only when the study is taken down to a particular area, that means I have to get a data that concern that particular state or region. So I can be able to give my report to that. But it's a work ongoing.
It's okay. Thank you very much.
Whatever suggestion you make now, we're also going to put it into practice and see what
it's okay. Thank you, Chinwedu, for this presentation. Just look forward, and I think what he observed, the observation he raised last, I think is very important, because whenever you are dealing with such kind of situation, there is need to know what will happen in the future. This is what will, and the government, the policymaker, are interesting, so that they can make more effort to plan ahead to cater for such problems. Thank you very much for the presentation.
Thank you.
Yeah. The next presenter is Victor Nawa is around with us.
So you can stop me from sharing.
Yeah, you can stop that, please.
Okay, I can stop sharing.
Yeah.
Okay, thank you.
Yeah, Victor Nawa, are you here with us? Hello, Victor.
Yes, I'm around.
Okay. I think Victor, you can take the floor now.
Thank you.
You can share from there, right? Or have you sent your slide?
No, I want to share, but I'm seeing it says host disabled.
Let me enable you so that you can share from there.
Okay, thank you.
So I have make you a host now. You can, it will be fine by now.
Okay, thank you.
I don't know, please, is Adeyemi Olu Akeju, is she with us here? Adeyemi? If Adeyemi is with us, let me know, please. You can unmute your mic to let me know, or you can chat me so that we can know how to schedule you next. Because your time has already passed, so but we use Chuedu to present on your behalf.
I can go ahead now?
Yes, Mr. Victor, you can go ahead. You have 25 minutes to do the presentation. Thank you very much.
Thank you very much. So what I am presenting this afternoon is actually joint work with Professor Nadaraja, and the title of the presentation is New Closed Form Estimators for the Beta Distribution. So my name again is Victor Nawa. I'm found at the University of Zambia in the Department of Mathematics and Statistics. So this is an overview of what I'm going to present this afternoon. So basically give you an introduction and a background, and then I will go into coming up with the proposed closed form estimators. Then I will look at the large sample properties, do some comparisons with other estimators, and then some conclusion and references. So here we are looking at a beta distribution. So suppose X follows a beta distribution with parameters alpha and beta. We know that the PDF for the beta distribution is given by that expression there, where the values of X are between 0 and 1, and alpha and beta are positive, where this beta of alpha beta is a beta function given by that integral. And then we also know that this beta function can be written as in terms of the gamma function. So given a beta random variable x, we know the expectation of x is given by alpha over alpha plus beta, and the variance of x is given by this expression here. So throughout the presentation, I'm going to be using sigma squared instead of variance of x, or this expression here, to represent the variance of x. So a short background, what motivated the research is that for a long time now, parameter estimation for distributions like the gamma, beta, Weibull, and so many other distributions required iteration methods in the sense that there were no closed form solutions. But recently in 2017, Ye and Chen derived closed form estimators for the gamma distribution, and the derivation here was based on likelihood equations of the generalized gamma distribution. And then Tamai, Iri, and Kubokawa in 2020 also derived closed form estimators for the gamma and beta distributions using what they called a score-adjusted approach. What was interesting was that the closed form estimator for the gamma distribution that Tamai, Iri, and Kubokawa found was exactly the same as the gamma closed form parameters found by Ye and Chen in 2017. And this was really more like what motivated us to do this research. And the idea was to see if we can come up with other alternative closed form estimators. So if we look at what is generally used, that is the maximum likelihood estimation. We take a random sample of size n from a beta distribution. Then we know that the maximum likelihood estimates are the solutions to these two equations, which, as we can see, cannot be solved explicitly. So here, this psi of alpha denotes the digamma function. And so these solutions, these equations cannot be solved explicitly because of these digamma functions here. So we can further show that if alpha hat and beta hat are maximum likelihood estimators for alpha and beta, then these estimators are asymptotically normally distributed with this covariance matrix here. So this covariance matrix here is a function of digamma, they're actually trigamma functions. So what we note here is we will use C generally to represent the sum of alpha and beta, and D as the difference between these two trigamma functions. E as well is a function of trigamma functions, and G as well. So basically, this is the asymptotic covariance matrix for the maximum likelihood estimator. Tamae, Iri, and Kubokawa's estimators are given here on this slide. So if we consider a random sample of size n from a beta distribution, then Tamae, Iri, and Kubokawa proposed these closed form estimators here. So basically, these estimators are functions of the mean of log of x over 1 minus x, and the mean of x log of x over 1 minus x. So these are the closed form estimators proposed by Tamae, Iri, and Kubokawa. And they also further showed that actually these estimators are also asymptotically normally distributed with the covariance matrix sigma there, which is given by this nice expression here. And it's a function of alpha, beta, and f. And f here is a function of these trigamma functions. Now I turn to our proposed closed form estimators. So here, basically the derivation it basically uses properties of expectations of the beta function. Actually, in our paper, we rederived the Tamae estimators using this same approach that I'm going to present to you this afternoon. So basically, these are the expectations for the beta distribution. So this one is well known. If we get the expectation of the log, we get this expression. If we get the expectation of log of 1 minus x, we get that expectation. And if we get the expectation of x log of x, we get that expectation. And similarly, the expectation of x log of 1 minus x gives us this expectation. So the idea now is we are going to substitute 4 into 6, and then get rid of these digamma functions and replace them by this expectation of log of 1 minus x. So when we do that, and similarly replace this alpha over alpha plus beta by the expectation of x, it turns out that we are going to have this expression here. And then when we multiply this expression 7 by alpha, we will note here that what we are going to get here will be an expectation of x, and then the alpha will be multiplying what is on the right-hand side of 7. And then we will solve for alpha. So when we solve for alpha, we get this expression here, 8. And then we get expression 8 and substitute it into 7. and then solve for beta. And when we do that, we get expression 9. And then by the weak law of large numbers, we can replace the expectations in 8 and 9 by their sample version, and we will get to this expression here. Are you able to get me?
Yeah, we are with you.
I'm hearing some.
Yeah, I'm trying
somebody
to
on the floor.
Yeah, let me check. I think it's from you. Well, you or Chuendu. Let me check. Chuendu, let me unmute her.
Okay.
And then, okay. I think
Okay.
it's okay now.
Okay, thank you very much. So this first expression here, number 10, represents our first set of proposed estimators. And now I'm going to move on to the second set of proposed estimators. So similarly, if we look at 2, 3, and 5, so this is 2, 3, and 5, we make a similar substitution. So we put 2 and 3 into 5, and everything here will be written in terms of the expectations in 2 and 3. And when we do that, we are going to get this expression 11 here. And then similarly, if we multiply this expression by alpha, this term here becomes an expectation of x. Here we are going to get a 1, and then alpha will be multiplying this whole expression on this side. And then when we make alpha the subject, we get this expression number 12. And then similarly, we get expression number 12 and replace it in 11 and solve for beta, which gives us expression number 13. And then when we use the weak law of large numbers, we get this second set of proposed estimators. The first theorem that we are looking at here is basically looking at the large sample properties of that first proposed estimator in 10. And here we show that actually these estimators are asymptotically normally distributed, and the covariance matrix is given by this expression here, where the variance for alpha hat 1 is some function of alpha and d. Remember, d was already given. And the covariance of alpha and beta is a function of alpha, beta, and a function of d as well. And similarly, the variance for beta is a function of d as well. So what I do here is basically take you through a proof, a sketch of the proof. So if we begin by letting x bar, y bar, and z bar to denote empirical means of x log of 1 minus x and x 1 minus x, we can get the expectations of these x, y, and z bars given by these expressions. Actually, these were already derived, so we are just rewriting them here. And then we can apply the central limit theorem to show that x bar, y bar, and z bar converge in distribution to a normal distribution with this covariance matrix. And then we go into this expression and evaluate each of these covariances and covariances. And some of them have already been evaluated, like the variance of x. So we will get, so these are the expressions basically. So a function of d, so the variance of y is a function of d, the covariance of x and z is a function of b, the covariance of y and z is a function of b and d, the variance of z is a function of b and d. And then we consider two functions here, g1 and g2. functions of x, y, and z. And we look at the expectation of x bar, y bar, and z bar to give us this expression here. And then we use the delta method. So when we use the delta method, we evaluate partial derivatives of g1 and g2 at x naught, y naught, and z naught. And we get this expression here, this matrix here. And then using the delta method, we can show that the asymptotic distribution of alpha and beta hats actually converges to the normal distribution asymptotically. So that's basically the sketch of that proof. And then similarly, we do the same thing for our second proposed estimator in 14. And we basically just follow the same procedure. So here we note that the variance of alpha hat 2 is some function of alpha, beta, and E. The covariance of alpha hat 2 and beta hat 2 is a function of alpha, beta, and E. And the variance of beta hat 2 is a function of alpha, beta, and E. And basically, the proof follows the same approach. So here we are using x bar, u bar, v bar to represent the empirical means of x, log of x, and x log of x. And then we get the expectations given here. And then again, we use the central limit theorem to show that x bar, u bar, and v bar converges to a normal distribution with variance, covariance matrix sigma. And then we evaluate each of these components of sigma. So these are the expressions here. We note that the variance of x remains unchanged. The variance of u here is E. The covariance of x and v is some function of A. The covariance of u and v is some function of A and E. And the variance of v is a function of A and E. Again, we use the delta method. So we consider two functions, h1 and h2, and we evaluate partial derivatives of h1 and h2 at the expectation of x bar, u bar, and v bar. And this is the matrix that we are going to get. So it's a function of A. And then using the delta method, the result follows. The next part here, we are doing a comparison of the estimators. And basically what we are doing here is we are comparing asymptotic variances of the maximum likelihood estimator of the TIK, our two proposed estimators, proposed 1 and proposed 2. And what you are seeing in the first graph here is a variance of alpha, where we are comparing the two proposed estimators. So we get the variance of alpha hat 1 and the variance of alpha hat 2, and then get their difference, and then look at the signs. So in this region above here, we have positive signs. In the region below here, we have negative signs, meaning that our proposed estimator 1 is more efficient in this region below here compared to the proposed estimator 2. And then we do the same thing. We compare the variances of alpha, alpha hat 1 and TIK. Again, we look at the signs, so the positive signs and the negative signs. And what we note here is that our proposed estimator is more efficient than the TIK estimator in this particular region here. So those are values of small values of beta and larger values of alpha. And then similarly, we do the same thing. We compare our first proposed estimator to the maximum likelihood estimator, and it's all positive here, meaning that the maximum likelihood estimator is more efficient than our proposed estimator. And similarly, here we are comparing the variance of alpha for our proposed estimator, that is alpha hat 2, to alpha hat TIK, again looking at the signs. So our proposed estimator here is more efficient in this particular region here. And similarly, we do the same thing. We compare the second proposed estimator to the maximum likelihood estimator, and the maximum likelihood estimator is more efficient. So we do the same thing for TIK versus the maximum likelihood estimator. Is a similar picture emerges from there. And then we turn on to variances of beta. So basically what we notice is that it's basically the same results that we get when we did our comparisons for alpha, except they appear to be in reversed order. So basically that's what we notice here, the regions. So how many minutes do I have, Chair?
If you can round off in 2 to 3 minutes, it will be fine.
Okay, so basically, let me get to the conclusion. So basically what we tried to do here was to propose an alternative closed form estimator that would be simpler than the TIK estimator. And basically what you see here are the results that are coming out of those tables where we are making the comparisons. And what we are seeing here is that our proposed estimators are a little bit simpler than the TIK estimators. And for certain values of alpha and beta, they can actually be more efficient. But as I said, this was based on a paper that we wrote with Professor Nadaraja. So if you are interested in more details, you can get to this paper and read more about it. Thank you very much.
Thank you very much, Mr. Victor Noah, for the wonderful presentation and timely. I don't know, to the floor members, if anyone has any question or contribution or observation, you can unmute your mic and direct it to Mr. Victor Noah so he can respond accordingly.
Okay, thank you. Thank you, Victor, for the nice presentation. Yeah, it's actually very nice. But I want to check just maybe your comment. And I've seen that with the estimators that you have been able to derive, you were also able to show some convergence of those, which I wanted to ask, but I see that now it's already captured in that. But with the application of the weak law of large numbers, there are also those challenges that and you, in terms of the convergence, I think you showed that it converges in distribution. So I wanted to check in terms of, does it also hold for almost a sure convergence, so that at least maybe you can somehow try to generalize these kind of convergences?
Yeah, basically, actually, we also showed that these estimators are consistent, which I think is really almost sure convergence.
Okay. And maybe the one last question is the rate of convergence. Did you check how fast is this convergence? Is it in comparison with maybe those that are available in literature? Thank you.
On that one, we did check. Thank you.
Sorry, maybe I just have I think few observations, especially on the closed form estimations. One of them is it that because I realize that the distribution the baseline distribution you use in the coming up with the closed form estimation are the gamma and beta. Is it that this kind of techniques for the closed form is only applicable to such distributions, or it can be applied to further other distributions?
Actually, we have written a number of papers now. So one was on the gamma distribution. We have written another paper on the beta distribution. We have actually written another paper on the bivariate gamma as well as multivariate gamma distribution, and it can be extended actually to many other distributions. The same idea can be applied.
Okay. So, and the main idea, the major idea is just to extend or to have a closed form of the parameter, the estimation of those parameters, or what really is the major concern?
The major concern basically is for most of these distributions, in most cases, people are interested in maximum likelihood estimators.
Correct.
But then for a number of them, it's not possible to find these maximum likelihood estimators in closed form, and you require these iteration methods, and sometimes you really don't get to get the true maximum values, and sometimes you require a lot of advanced computational skills. And so the main idea is to try and save researchers time in such a way that you get this closed form estimator, which you can almost immediately find as long as you have all the right expressions in place.
Yeah, because in most of the cases about the issue of the maximum likelihood, there is some situation that we realize that the functions of the maximum likelihood are non-linear, and they are very difficult, to get the value. So in such situation, we just assume that we can use the numerical computation in order to have that values. So in this case, if we have the closed form of those kind of distribution, what you are saying is that it will be more easier for us to compute the value of the parameter when when compared to the situation of maybe if they are not available. Is that okay?
Yes, basically that's what we are saying. Because generally you observe for most of these distributions where it's not possible to get closed form maximum likelihood estimators, you notice that for some of them, it is possible to get the method of moments, the method of moments estimators. But then you notice most of those method of moments estimators are not efficient. Like you find the variances are quite huge. So the asymptotic variances, and if you compare those to the maximum likelihood asymptotic variances, there's usually a very huge discrepancy. And so the idea is, can we come up with alternative closed form estimators that would lead us to finding quick solutions to most of these distributions?
Okay, Victor Noah, thank you very much for the explanations. I think it's very clear and knowledgeable, and people definitely will look at this direction of looking the closed function, so it will make it easier to get such parameters that are nonlinear or that they are difficult to obtain. Thank you very much. We look forward to work together, and
thank you.
I think we can call it a day.
Thank you very much.
I don't know, please, is Adeyemi Olu Akejos with us now? Adeyemi Olu Akejo from University of Ibadan. Okay, so I think maybe she's not with us now. Maybe the best thing is because the break time is almost close by. So because we intend to go break by 4 o'clock, but in absence of the next presenter, we can go take a short break. We will come back in 10 minutes. I think this is 3:53. So we'll come back in 10 to 15 minute time. Let's say in 15-minute time. Thank you very much.
Sorry for this. We don't even know here.
Hello?
Yeah, hello, Mr. Monday.
Yeah.
We are coming back in a few minutes. I think
Okay.
it's almost 10 minutes after.
Okay. Thank you.
So maybe in a few minutes. So I think you are also ready for the next. Okay, you be the next, right? You are ready?
I told them to share my slide from your end here.
Okay, you submitted your slide, right?
Yeah.
Okay, so I'll check. Hi, Quinsley. Dr. Quinsley?
Yes, I can hear you.
Okay, can hear me, right?
Yeah.
I think we can
Let's proceed.
proceed, right?
Yeah.
Um, Dr. Is it Adeno Monday, right?
Yes, you can. Yes.
Yeah,
You
yeah,
can
which
call me
was
Monday.
right. I don't know if Adeyemi Olu Akejo is here with us or Mark Johnson.
Yes, Akejo is here.
Akejo, you are here? Akejo?
Yes, I'm here.
Yeah, what happened? Because we have been waiting for you the last, your time has already passed.
Yeah, I sent a mail. Where I couldn't get access to internet.
Oh,
so
sorry.
I have to leave that location to another place.
Sorry about that. So now, can you present now? Though the next presenter should be Adam Abubakar Umar, but we can allow you to present if you can round up in the very timely time.
Okay, yes, I should.
Okay, we'll give you just 20 minutes to do that.
Okay.
Is it 20 minutes? Quinsley, what do you see? Can we give him 20 minutes?
I think we should give him his full time, 25 minutes.
No, if you will have the full time, then someone will lose his time,
Okay.
Because already their time has passed. Now the next presenter is okay. Since Victor Nawa has present on his behalf, then I think we can. Okay, no problem. You can have the 25 minutes, no problem.
Okay, thank you.
So can you share from there, or you want us to share from here?
It's disabled.
Okay, let me elaborate. No problem.
Okay.
So it should be fine now. You can share now?
Okay. Yeah.
So Adeyemo Monday, you will be the next speaker after him.
So please just let me share my.
Akejo, can you can share now? It's fine, right? Hello, Akejo. Okay, Joe, you can just enlarge the screen. You can enlarge the screen and it will be fine. No, no. Yeah, okay. Good. Hello? Kejo, can you hear us? Can you unmute yourself? Because I don't know, we can't hear you.
Is he muted?
I don't know because he's not muted. I can. Hello, Akejo? Akejo, we can't hear you.
Can you please hear me?
We can hear you now. Fine, we can hear you now.
Okay,
You can also hear me, right?
I can hear you perfectly.
Okay, that's great. So you can move on, please. Your time started now.
Okay, thank you very much. So thank you very much. Good afternoon to everyone. So my name is Adeyemi Olu Akejo. So I'll be talking on.
Hello, Akejo?
Yes.
Hello?
Hello.
Yeah, your voice sounds very low.
Okay, I will try and increase my voice.
Now is fine. Now is fine. You can move on.
Okay, thank you. I will have to talk a bit louder. So thank you. So I will be talking on Malavin calculus computation of the Greek theta and vega of Asian and base of asset option. So so thank you. So the abstract is so in this work, what we try to do is to determine the theta and the vega sensitivity of Asian option and the base of asset option, and we use the properties of Malavin calculus. So the sensitivities are represented by degrees. So we call this sensitivity, we call it degrees. And the degrees are determined with respect to the parameters of the underlying assets. And here in this discussion, we like to look at the properties of the Malavin calculus, which include the scored integral, the integration by part techniques of the stochastic variation. And then in that calculus, we're going to try to obtain the weight function, which will help us to obtain the an expression that represents the value of the best of asset option and the Asian option. So, so in this talk, our objective is to consider the Greek theta and the Greek vega, and also on an Asian option and the base of asset option. So we say the degrees represent the price sensitivity of a derivative with respect to changes in underlying parameters. So in this respect, since we are looking at theta and vega, theta, in this case, the parameter we're looking at here is the time to the expiration. The beginning, the time, capital T, when the contract we terminate. So that's about theta. Then also, theta theta increases when the option is at the money, and it decreases when the options are in and out of the money. So we say the long call and the long put, they normally have negative theta. So this is the general behavior of the Greek theta. Why for the short call and the short put, the value is always positive. So now on the other hand, for vega, which is the measure of the value of the option with respect to the volatility. So the vega indicates how the option price will change, given a 1% change in implied volatility. And an option with a vega of 0.05, for example, shows that the option value will change by 5%, but 5% if the implied volatility changes by 1%. And then there is a likelihood that underlying instrument will always experience an extreme value if there is an increase in the volatility. And also, if there's a rise in the volatility, it will also lead to the rise in the value of the option. And conversely, we say the option value will be negatively affected with a decrease in the volatility. And that we have experienced, for example, in Nigeria of recent, where we have the exchange of the naira to dollar always on the increase. So we can look at that as one of the concepts to consider here. Now, so suppose that an investor owns a call option with strike price K. Then if at tau, time 0, is the time when the call option was acquired in the first place. And we say S of tau is the price of the underlying asset at tau. Then if at maturity, at time T, then if S of T is greater than K, where K is the strike option, the strike value, then the option is in the money. If S of T is equal to K, then the option is out at the money. Then if S of T is less than K, then the option is said to be out of the money. So these are the concepts that we use in this discussion. Now, Asian option and base of asset option, they represent option that has multiple underlying assets. And that is our major objective, to look at those options that have more than one underlying asset. So Asian option, in the Asian option, the way the behavior of Asian option is that the average of the assets underlying the contract over a certain period of time, and determine if there is a profit when compared with the strike price. So we look at that from the work in 1 and 7. Meanwhile, base of asset option is the time that consider the maximum of the underlying asset price in comparison with the strike price. So if we have 2, 3, 4 values of the option of the underlying asset, we compare each of them with the strike price. The one that is the maximum represents the value of the base of asset option. Now, the dynamics of this pricing and of option is such that at maturity, there's a flow, which we call the payoff, and this flow can be guaranteed by the option owner. So then the option owner can purchase with premium portfolio that has equal flow of price with one of the options. Now, in this pattern, we call that to be, we say, this is possible if the arbitrage opportunity is excluded, is taken away from the system. And if that is the case, then that means that option is self-financing. So we say it is self-financing, and that becomes a dynamic strategy. That is, the option can sustain itself. The profits acquired from the option can be plugged in again into the market to continue to trade. Now, to determine the value of theta and vega sensitivity, so we use the principle of Malavin calculus, as we mentioned earlier. And this is a calculus that has to do with the integration by part techniques or the stochastic variation. And we also here we use the calculus to derive the expectation of the payoff function of both the Asian and the base of asset option. These are the two options we're looking at. Now, the simplest way, coming to Malavin calculus now, the simplest way actually to compute sensitivity is often by Monte Carlo method. And this method consists of approximating the derivative by the incremental ratio, which is obtained by simulating the payoff corresponding to the closed value of the underlying asset. Now, what we discover is that these techniques of the Monte Carlo is actually not efficient, particularly if the payoff function is not a regular one. An example is the payoff function of a digital option. So this problem can be solved by integrating by part, and by differentiating the density function of the underlying asset. Now, in a more general setting, Malavin calculus allows us to obtain the explicit integration by part formula, even if the density of the underlying asset is not known. So it gives us an effective tool to approximate the Greek numerically. So now we have, these are the concepts that is being used in Malavin calculus when it has to do with application in finance. Now, One of them is the Clark-Ocon formula. So this is an assistant, it's a formula that we use often. So now this formula play an important role in the application of Malevin calculus to finance. And what they do is that it helps us to improve the martingale representation theory. And it allows us to express the hedging strategy of an option in terms of the stochastic derivative of its price. I will come back again to that Clark-Ocon formula. Now, we consider a Malevin differentiable random, the space of Malevin differentiable random variable, that is that D12, and actually it's also a square integrable space. So if you pick X, so X is a variable that is defined in that Malevin differentiable random space. And that X is such that we have a sequence, Xn, that is in X, where that S is a closure of that our Malevin differentiable random variable space, such that the X is the X become the limit of that sequence. And the limit of, so D here, we introduce this D. So the D here is the Malevin derivative of the variable X. And so this D of Xn, we say it is a square integrable function that exists in this space. And so we define that dx in this form, where dx is the limit of ds of n. And so this defines the Malevin derivative of x. So that we need in order for us to discuss our payoff. Now, we also consider another concept of Malevin calculus, which is the chain rule process. Now, if I have two variables, x, y, that are Malevin differentiable variable, random variable, then what we observe is that the product of the two of them is not square integrable. That means it doesn't belong to their space. And so in order for us to deal with this kind of a situation, we consider a smaller space that is close on that product. And that brings us to the idea of a D1 infinity. So this is a smaller space that's with, so this space now, the product of these two variables x, y can be obtained in this space. So we take a function phi, which is infinitely differentiable function, and it has a polynomial growth over R, such that if x is in this differential domain, then the phi of x is also there. And that means that, so we can talk about here the chain rule process apply here, such that this equation is satisfied. So differentiating that function means that we take the derivative of that variable, then we take it also on that the function itself. And so this concept can be extended to multi-dimensional case. As a matter of fact, this extension is what we actually work on. So we'll be working on this multi-dimensional situation. The one-dimensional space is in existence, but we try to extend this to multi-dimensional case, because it want to fit in into the kind of the options that we're dealing with. And if one-dimensional case exists in that domain, then we also can prove that the multi-dimensional case also do exist. Now we're also coming back again to the Clark-Ocon formula. So as we mentioned before, that it's supposed to improve the mathematical representation theory. And this theory asserts that if I have so that
if you are far away, okay, Joe, from your mic, we can't hear you.
Dr. Akejo, we can't hear you. We can't hear you anymore. Can you raise your voice, or you should come closer to the mic, please? Hello, Dr. Akejo, can you hear me? Dr. Akejo, can you hear me, please? Maybe his network.
Yeah, but we can't hear you. I think it's writing on the chat, but
Maybe it's the network problem, because actually that is why he's not been able to present the other time, because he complained of the network issue from his location. Yeah, this is a general problem. Dr. Monday Adenomo. It's a general problem. None of us can hear him. We think the problem is for him exists about keeping everyone waiting.
Is he responding with the text?
Yeah. I can see he respond with the text. Probably is a problem of network. Maybe have it to exist avoid keeping. I think that's the best option for us, right, Quincy? Dr. Kunsley, I hear he responds to all that maybe there's a network problem, so he existed so that he can give space for others to move on. So I think since we have an issue with that, if he can hear us, thank you very much, Dr. Adeyemi Olu Akejo. At least we have got your concept, and we got some insightful information from your presentation. Thank you very much. So I think we can move to the next person. Who is Adeyemo Monday? Adeyemo Monday, are you close by? Hello, Monday. Hello, Dr. Quinsley.
Yes.
You can hear me, right?
I can.
Yes. I don't know. I think we have already chatted with him, so he exists. I'm calling on Monday Adeyemo. I don't know if he's close by.
Monday is around.
Adenomo, yeah, he's online. He's with us, but I cannot hear him. Maybe he's not close by. I don't know. If he's not Adam Abubakar Umar, I think, and just present. But I don't know if he's around. Let's give him a chance. Okay, you are here. Okay, please unmute yourself. Unmute yourself. You already unmute yourself. Can you talk? Can you speak to us?
Allahu Akbar, Allahu Akbar, Allahu Akbar.
Hello?
Hello, Monday.
Hello?
Monday.
Can you hear me?
Yes, we can hear you. We can hear you perfectly.
Okay, great.
Yes, you are ready to make the presentation now?
Yes, but I sent my slide to
Okay,
what's his
okay,
name?
okay. You want us to share it from here, right?
Yes, so that there will be no problem of network.
It's okay, no problem. Let me check.
Okay. Yes, number.
Hello?
Yes. I can see your screen, but I've not seen the slide yet.
Yeah, I'm trying to
Okay.
share it.
Maybe I should be talking a little before we bring out the slide.
Can you see the slide now?
I can see it.
You can see it now?
Yes. I can see the slide.
Okay.
Good evening from Nigeria. I really want to appreciate the organizer of this workshop. It's a very great initiative. Already we know that the world of science and world of the academics, we need collaboration. Once again, I thank the organizer for the opportunity. My name is Monday Osaigi Adenoma. My area of research is econometrics and time series. But I'll be looking at this topic, the art of prediction in Africa, evidence from time series and machine learning techniques. I've been in the area of time series, but with this era of data science, I'm trying to migrate towards the machine learning. So if you look at the slide 2, these are the things I do. These are some of the things I do. I don't want to take much of our time. Maybe during the discussion we can talk more about it. But my study, I studied in Nigeria. All my degrees are in Nigeria. Though I've made some short travel to Malaysia, to Germany, and just few places. But we'll be looking at time series. Though most of my research have been using data set in Africa, especially that of Nigeria. But what about time series? We know that time series has been generated in volumes in the continent of Africa. talk about rainfall, talk about temperature, talk about stock prices. Now, one of the major purposes of time series and machine learning techniques is for prediction. What we do is that we try to understand the past behavior of time series data sets and then use it to predict the future. The data have to learn from the past and then forecast into the future. Those of us in time series, we know that we have what we mean by in-sample forecast. We also have what is meant by out-of-sample forecast. But most of the, before now, most of my prediction, I've not been looking at this area of dividing the time series data set into these parts, the training part and the testing part. And this way of analyzing time series data set is very suitable because I remember when I attended one interview in the Central Bank of Nigeria, they were telling me that sometimes we statisticians will just forecast, but our forecast many times or sometimes it could be far from reality. Well, I think maybe because one, I've not been looking at this area of why not you divide the time series part into two parts, train the model with the data set, then the appropriate model, then use it to test the model using the data you have kept for out of sample. Then the next slide. The time series, it could be regular, it could be irregular, but one of the popular time series model is the Box and Jenkins. So we have other methods like exponential smoothing, we have hot winter forecasting and other methods. Then we'll come to the uses of time series. Time series is very useful. As I mentioned before, if you see the second one, it's very useful in forecasting. Then we can use it to understand past behavior of variable. It can also be used to analyze, evaluate current achievements. It can also help in making comparative study. Then the application of time series, that is, slide 6 now. Time series is applied in virtually all fields. We can see it in the field of engineering. You can see it in the field of geophysics, business, and all that. Like most of my research interest is in the area of economics and then finance, even though I'm in the Faculty of Science. And these data sets are very much available in Nigeria, like that of the finance. We generate data sets from the stock market. Economists to the MBS generate information on GDP, unemployment rate, and all that. Then in agriculture, we also have data sets there too. Then another thing that will interest us is that we have what is called the univariate time series, and we have the multivariate time series. But this talk will be focusing on the univariate time series. But the univariate time series, one will want to model just a single variable. But if you find out that there are other variables that can help predict this variable of interest, one can use what we call a time series model with exogenous variable. It's not a multivariate, but you're trying to use other external variable to help forecast this variable of interest of yours. And in page 8 now, or slide 8, we can see the way we bring in exogenous variable into this model. We have what is called time varying measurements, such as inflation. Somebody want to look at how does inflation affect unemployment, or how does inflation affect interest rate. But in this case, you are interested in interest rate, but exogenous variable is coming from inflation rate. Then we can also bring a categorical variable. They can also bring in the dummy variable. Like one of the work we did during the COVID, we tried to analyze the Nigeria stock exchange market. They're looking at the effect of COVID-19. But we brought in COVID-19 to the model as a dummy variable, such that when there's no COVID, we say that is 0. When there's effect of COVID, we say that is 1. It becomes dummy. Now, why do we incorporate exogenous variable? The next slide, slide 9, it can provide more accurate prediction. It can be used for causal analysis. It can also help in forecasting. Then it could just be a kind of a propelling, a kind of an idea to say, okay, maybe this may be very useful in the context of multivariates. Then the ARIMA, this is a popular ARIMA model, such that many times the time series variable, especially that of the economic time series variable, are not stationary at level. Then we can find the first difference and then model it with this. Then the extension is just, in this case, it's also ARIMA, but now we're bringing the exogenous variable into the system. Now, if you look at the page, slide 11, you see that we are bringing X. The X is the exogenous variable. We could explain the endogenous variable, which is the variable of interest. We have published one work in a book chapter. Now, in recent time, we in Nigeria were trying to embrace the big data, the machine learning, artificial intelligence, and all that. Then we are encouraging ourselves that even though we are in any area of statistics, like me, I'm in econometrics, or sorry, time series, but we need to still embrace the machine, the data science aspect of the data science and the artificial intelligence. For me, I'm just focusing on the machine learning aspect. But the machine learning aspect also has some advantage, which will be seen in the example I illustrated in this talk. But the great thing about machine learning is that the method learn with the data set. And the good thing about it can be doing what is called sampling. If you are take every 10 observation and then model and do a lot of models, it learn a lot, and then the best model will now be used to predict into the future, so that the prediction will now be compared with the data you have kept for the testing. They can now compare the actual prediction with the actual data set, and it's a good way of modeling and forecasting. Then the major parts of machine learning, number 1 is for forecasting. Then the other part of it is for classification. Can you hear me?
Yeah, we can hear you.
Thank you very much. Then it's for forecasting, the first part. Then the other part is for classification. And we generate data in terms of the classification part. Even in Nigeria, you can have data set on HIV case, which HIV, yes, maybe positive or negative, that is binary in nature. You can also have situation whereby you can classify into categorical, maybe high, low, and mediums. That can be used in classification. And those of us that use some of these methods, you see that the machine learning can handle the data that are in classified nature. They can also handle data that are metric in nature, like parametric in nature. Now, in the machine learning context, we have some divisions. We have the supervised learning, unsupervised learning, and reinforced learning. For now, I'm still working on supervised learning. The supervised learning have the classification part and the regression. The illustration we'll be showing here, we'll be dealing with the regression part. Then we have so many of the techniques in terms of machine learning. We have the artificial neural network, random forest, decision tree, support better regression. We have many Bayesian, KNN, and all that. But for this talk, we'll just look at these examples I've mentioned here, these 4 of them. Now, because I'm a teacher also, we can't be complaining all the time in the developing world. This is what I tell my students. that sometimes to get some specialized software, they could be very expensive. Yes. And since we don't have access to those, although sorry to say, in our own country, you have access to pirated copy, but all the same, we're trying to encourage them to open source software because some of our students they leave Nigeria to come out there to UK, to other countries to study. And we know that some of those advanced countries use open source like R, like Python, like Julia, like Scala, and all that. We try to encourage them to use open source, but I'm much more comfortable with R. We have that to do machine learning, we use open source like R to do it, and it has a lot of advantages. And it can be, I teach my students that you can download them, it's free of charge. It can be download to Mac, it can be download to Windows and all that. And you can install packages that you want to use. This is a classical piece of Arrow console. Now, in time series, because I'm just trying to explore the world of time series. That's most of the time what I do with R. I like to look at most of those packages that can analyze time series data set and financial time series data set. I've used these packages like T series, LM test, forecast, and F basics. Though the time series one is the T series and the forecast are for the time series. The LM test is just to test the parameter, whether that's significant. F basic you can do something like normality test and all that. Then in financial time series, because I also belong to, I also do work in financial time series. I use the Rugash. The Rugash is very versatile in terms of the very time series. It has a lot of versions. One of my first PhD student in my university, we used that. We did a work on total. We used time series data, financial time series data set from total, and we got the work published in Financial Innovation. Now, when it comes to financial, the machine learning now. The machine learning, I'm interested in the carrot package because the carrot package has a lot of machine learning techniques. Because of time, I won't spend much time here, but I just want to tell us that the carrot package is very versatile in terms of machine learning. Then the source of data set we'll be using here, we're using Nigeria, just as I call him Sarah, the person that I met with him before. Maybe it's not here. We want to collaborate with African. Let's use African data set, of which I am following suit to. Most of my work I've used Nigeria data set. Sometimes people complain that sometimes we use Nigeria data set, sometimes it doesn't get much citation. Sometimes it doesn't get it published because people may not be too interested. But the same, we still need to continue with our data set. We know that one day it will be appreciated by other researchers in other parts of the world. Then in the data set, we divided into two parts. The first, we divided 80% for training, 20% of data set for testing. Then we use this statistic to measure the performance of this model, like the mean absolute error, the root mean square error. The data set we use, as you've seen there, this is the view of it. The head tells you the first 6 observations, there's the beginning of the part of the observation. The tail tells you toward the end. In this work, we have about 22,593 data points. That is the plot. You can see, but our focus here is the price. The price is like, we want to focus the price. This is a financial time series data set. The price is the closing price. We want to see when the market at the beginning of a daily market, you see that there's low, there's high, there's open price. But the price you see here is the closing price, which is the final price for the day. You can see from this plot, you can see the low, the high, the open, the behavior tends to follow the same behavior of the price. Then we use those machine learning techniques and also the time series. The time series is the RMAS because we're looking at, we want to predict the closing price, but we're using low, open, and high as exogenous. The same thing with the other machine learning technique, that's what we do. If you look at this in sample forecast, we see that the model with the technique with the lowest mean absolute error and least square error is for neural network, followed by the RMAS model. If you come to the out of sample also, this out of sample is that the prediction, we use it to compare the actual. We also see that the neural network perform better, followed by the time series. We see that all the same, the machine learning is doing well. We see that the time series techniques too is not also doing bad. To wrap up now, the good art of prediction is to divide the series into two parts, testing and training. Then for the result, we found out that neural network dominated, then followed by the time series model, which is the RMAS. But decision tree perform poorly. So we also have we also have other methods we can use. So for this talk, we just decide to use this. Thank you so much.
Thank you very much. Thank you very much, Dr. Adeyemo, for the insightful presentation. We really appreciate. To the members, if anyone has question or observation, can please unmute himself and raise the question or observation to our presenter.
I have a comment to just reinforce what you said. There's something you said. Thank you so much for the wonderful presentation. Very interesting, and it's also an area that I love working on, although I've not really published much on using AI machine learning model, but I've done some working papers on that. And I love the fact that you said we should use our data. They might say using our data, it may not get a lot of citations, but one day others will take notice. And I love that comment. It's really encouraging to actually pinpoint that we need to tell our own stories, and our own stories is by using our own data, even if maybe we might use other data, but for comparison purposes. But it's critical that we begin to use our own data to actually tell our own stories. Thank you so much.
Thank you.
Is there any observation or question or anything from someone? Thank you very much, Prof, for the presentation once again. Okay.
Although we don't have much participants here, but I want to say that actually collaboration is what we Africans are longing for.
Yeah, right.
Because of the economic situation, researchers can be busy.
Exactly.
Like recently, I reached out to somebody in Nigeria. He say he's busy and all that. Another person say maybe another person from another African country say is also busy. But it's good enough. Somebody now got to me. He said there are a group of people. They are working in machine learning for data set from civil engineering and all that. What I want to say is that we have some good African researchers, but for them to be well exposed, I think the collaboration would really do well for us. That's just what I want to note here.
Yeah, thank you very much, Monday. And what you raise is one of the main objective or even goal of setting out this workshop, which will go a very long way. And as you know, attended previously, Prof. Sarales, who is here in the UK, he always encouraged and he's 24 hours ready to see how he can collaborate with African researchers in order to improve on the African research. And we are hoping of more people like him to dedicate their time in assisting the growth of this collaboration. And at the end of this workshop, we'll come up with a very an important forum that will maintain a serious collaborations in order to improve our statistical research activity, especially in the African continent. So nevertheless, immediately after the workshop, I'm sure the the committee will look forward and come up with some insightful suggestions on way forward. And we hope that everyone will be part of it. Thank you very much for that. We truly appreciate, and it's well noted. Thank you. Dr. Quinsley, do you want to add anything, or we can move on?
No, we can move. You've said most,
Okay.
but I'll contact him later to know more about collaborations.
It's okay, no problem. So
Mm.
thank you very much. I think there is one presenter, Adam Abubakar Umar. So I think we can go ahead, and later on we have our lead, our general discussion by our own Dr. Edson Utazi, which I see he's with us since morning. Thank you very much, Doctor. I can see you are still with us. So very soon you will give us your insightful comments on the topic. Says ways that professional statisticians can further encourage academic researchers to key into studies that address practical problem faced by industries and other sectors, those contributing to the development of solutions that have a direct impact on decision-making process in Africa. This is a very great topic, which Dr. Edson Otazi will give us after the last presenter. So let's move to the next presentation, which is the last one. Then it's okay, right?
Are you trying to open a?
Can you see the slide?
We can only see the different files, but you've not opened a document.
Okay. Okay, a minute. Can you see it now?
Yes, we can see.
Okay. So it's okay, right? You can see it full.
It's not full. Maybe you do full.
But it's okay. I'm sure you can see the.
It's okay. Yeah, it's okay. It's
We
a good
can,
presentation.
we can just move on, I think. Well, thank you very much, all of you, for attending this workshop. And we also thank the organizers for organizing this great workshop. which of course give us a room in order to have more collaborations and understanding and the way to improve our statistical research, especially in Africa. Thank you very much. My name is Adam Abubakar Umar. I'm here to present a brief topic with title An Extreme Value Modeling of COVID-19 New Cases in Nigeria. This is the title of the talk. And here are the overview. Here is the abstract. On the abstract, the main goal of this is to come up with an extreme value models of new cases of the COVID-19 pandemic in Nigeria, which is provided in this. The method is to use a method of extreme value, which was defined as the monthly maximums of daily new cases reported. So a generalized model, a generalized extreme value model distribution will be adopted or will be used and fitted to those data. The model entirely is a generalization of three distribution, which is the log normal and the two other distributions. So in this, using this distribution, the main purpose is to observe or to model some extreme value data. And these data, which are going to be considered here in daily data of Nigeria from 2020 to 2023. So the generalized model allow two or three parameters to vary linearly, quadratically with respect to the month number. The new cases of the COVID-19 in Nigeria initially increases and later increase significant downward or decrease in the monthly maximums. The efficiency and adequacy of the fits were assessed by some statistical properties, probability plots, and Kolmogorov tests. The model was used to drive the contours of the monthly maximum of the new cases, as well as the limits when the month's number is taken to infinity. So we have a brief introduction here on the case on the COVID-19 itself, which, as you so know, that the COVID-19 pandemic was still ongoing with varying level of impact and responses in different regions around the world. The COVID-19 itself continued to be a public health concern in Nigeria, as it was in many parts of the world. The implementations of this, the lockdown, mask law, social distance initiative, and vaccine drive were among the measures adopted during the spread in order to cater or control the spread of COVID-19. So we have a proposal on a way to address this global challenge, which we say there are so many papers that are published on daily new cases and daily new dates of the COVID-19 pandemic. But the often interest herein is with using the extreme value related to the variables. So here we have a recent work on COVID-19, which covers some African countries, which is done by Nadaraja and Ojo in 2023, which is the first paper on extreme value analysis of daily new cases. They provide an analysis for daily new cases in West Africa using the generalized extreme value distributions, accounting for trends in data. They define the extreme value as the monthly maximums. According to Nadaraja, we have this equation 1, which is the generalized form of the extreme value of 3 different distributions. So, and we have the limit of all those distributions, and equation 1, as we said, is the generalized extreme value model. Nadaraja and Ojo fitted the generalized model to data from West Africa, and with its location and scale parameter allowed to vary linearly, quadratically with respect to the month either. The interest here is to model the data, and is the structure of the data or the behavior of the data will give us an insight on which of the models to be used. So we say in this study, the generalized model will be fitted to the Nigerian COVID-19 new cases data with location and scale parameter, which will be allowed to vary linearly and quadratically, or based on the data, or based on the trend of the data, and it's with respect to the month number. The fitted model were employed to infer quartile of the monthly maximum of Nigerian COVID-19 new cases, as well as the when the month number is infinity. So here we have the data is a link for the daily data, which are updated on daily basis. For those that are interested, you can have the data through this link. So this is the map of the country, Nigeria, and this is the result, the summary statistics of the result we have. You can see from the summary, we have the maximum, we have the minimum, we have the first quartile, the median, and the mean, as well as the skewness and curtices. We said, according to table 1, there are some months without any report of COVID-19 in Nigeria. The first quartile and the third quartile were also reported, and the value are given here as 186 and 892. The value of the COVID-19 cases, the average value was also given as 698.1. So, and we have the scatter plots you can see in the next slides, which shows, you can see from the scatter plot here with the lowest smoothing of the monthly maximum, you can see it's showing a linear trend from what we have here in the plot. So through this, we now come up with a model that will monitor the occurrence of this COVID-19 new cases. From there, we use this model to fit in the data and come up with some reasonable suggestions that will help decision making. So we have here, we say that taking the value as a random variable, and the X here, it's representing the monthly maximum. You can see that according to Ojo and Nigeraja in 2023, we come up with another model, which we said that here, you can see here in equation 2, to address this setback and produce a better fit. We account for the trend in the COVID-19 new cases in Nigeria, as discussed in the data presentation section. The proposed model are fitted as follows. Look at the first one. We have the first model. The first from this equation 1, the first you can see, we have the function which is expressed as a constant model, which is the same thing as the extreme value model. Then the second equation here, you can see here, we call it the linear location model, where the linear location model here, we have an additional parameter on the first, on the location parameter, where we added another parameter there, you can see. We have another model which is called the quadratic location, which is given here in equation 4. Then we also have the linear scale parameter, which is given here in equation 5, and the quadratic scale parameter, equation 6. We also have the linear location and linear scale, as well as the quadratic location and linear scale. And finally, we have the linear location and quadratic trends, quadratic location and quadratic scale. All these are using to take into account all the nature and the trend of the data. And after fitting all this model, we now found out among the 9th model, which of the model can best fit the new cases data in Nigeria. So this is what the idea is. So after that, we have the proposed the 8 models, which is from equation 2 to equation 10, were fitted using the method of likelihood method here, as you can see here in equation 11. Where we now take the likelihood function, and we have all the parameter, all the estimates. So based on the computation, we say for the purpose of this presentation, we have some few computed values will be provided as discussed in the methodology. We said here, you can see that we tested for the independent because we believe that we assume that the data are independent. We have tested and we have the value. We have fitted the proposed model, and we from the fitted models, because we have 9 models which are all fitted here. Interestingly, you can fit when you fit all the model, we say that it is interesting to note that both the approach led to the same model. Whether if you like you add a parameter or you subtract a parameter, but you end up having a same model. This reveals that the significance or non-significance of adding or subtracting parameter from the term were determined by the likelihood ratio test by comparing the computed likelihood values. the archaic information criteria, and the Bayesian information criteria. So the value of the estimate are given here. You can see the value of the parameter estimates. You can see here we have the first parameter, which is A1, and as given as this, and the standard error is this. The second parameter A2, which is here, and the standards error value are here. You can see all the values here, the AIC and the Bayesian estimate, all the values are here, are computed here. We also have the probability plot of the best fits model for Nigeria, which is provided in figure 3. So let's move to figure 3 to look at the fitted value. Look at it here. So we have the probability plot for the best, which is the linear location. After plotting all the 9 models, the linear location, the linear scale, the quadratic, we now realize that this model, which is the linear location, gives the best fit for modeling the Nigerian situation. Also, we have the fitted model here, which we have the quantile function here. We have the 2.5, the 5, and the 50, 95, and 95% percent quantile functions versus the month number for COVID-19 in Nigeria. So we all have this plot. You can see from here that there is a trend of a bit an increasing trend for the Nigerian data. So here the explanation will say, according to figure 4, the plot of this percentage functions versus the month number was shown for the best model, which is the linear location for the COVID-19 in Nigeria. The monthly maximums is steadily increased with respect to the month number, and shows that the location increased by multiple of the exponent of the function of the parameter A1, which is here, for every unit increase in the month. So we say additionally, according to the computed value of the asymptotic limits of the Q quantile percent quantile, the limit is tends to be 2 as the month number is taken to infinity. Hence, the computed value of the asymptotic limit of 50, 95, and 97.5% quantile appear to be infinity for the Nigerian case. To round it here, we said that an extreme value model of the new cases of COVID-19 pandemic in Nigeria is provided. This method, or the method of the extreme value, was defined as the monthly maximum of daily new cases reported. The generalized extreme value was adapted to fit was adopted and fitted to them, allowing the 2 of its 3 parameters to vary linearly, quadratically with respect to the month number. We have modeled the monthly maximum daily COVID-19 new cases from Nigeria using this generalized model. 2 of the 3 parameters of this distribution are allowed to vary linearly and quadratically with respect to month number to account for the trend. The Nigerian new cases exhibit a positive trend. We have provided an estimate of the 2.5, 5, 50, and 95% quantile for Nigeria for up to January 2025. That is for the prediction or for the future use purpose. And we have also provided the asymptotic limit of this quantile as the month number approaches to infinity. We said the goodness of fit is also the goodness of fit's model was also examined by using the probability plot and the Kolmogorov test. As you can see, we have all the values. It is of concern that Nigeria did not exhibit significant downward with respect to monthly maximum of daily new cases. It is also concerned that the asymptotic limits of the 50, 95, and 97.5% quantile are infinity. So the governments of Nigeria may wish or may want to take an appropriate action to reduce the new cases of COVID-19 with regard or with respect to monthly maximums. And here we have some of the references, and we say thank you for listening. Thank you very much.
Thank you very much for your presentation. Are there questions?
So, like when you say the 97.5% quantile, like what do you mean by that, for example? In terms of the estimated amounts of cases for COVID-19 in Nigeria.
Hello?
Yeah, can you hear me?
Yes, sorry. Please come again, you said.
Sorry, could you just explain, like when you say the 97.5%, like the broken blue line, for example, what is that? Like, can you explain a little bit what that means in this example, in terms of the cases in Nigeria?
Yeah. So from this figure, you can see that they are all estimates. Because the quantile functions, all the idea is for us to also estimate just like the confidence, the goodness of fits, because the interest is to fit. And here the idea is we have on different quantile function or on different percents, where you consider at the 50, we consider at 95 and also at 97, in order to make sure we have the estimate is perfect. Or the estimate, we can say that we have almost a 95% or assurance of our prediction. So it just gives us an insight on the effectiveness of the performance of the model and also the reliability of the prediction. So that is just in brief.
Okay, yeah, that's what I thought. Could you explain about, you said something about the limit being 2. Could you explain that again one more time, please?
Yeah, the on the limits we are considering the infinity. When the extreme value is getting larger, it's maybe it's approaching infinity. We said that the limits, the limit tends to 2. You can realize that as it's getting larger, it's approaching infinity. The limit it's getting a bit smaller.
So what is 2? Is that the number of cases, or what does 2 mean here?
Hello?
Yeah. I'm just asking, what does 2 signify? Is it the number of cases?
Okay, yeah. She's here, right?
Yeah, okay.
Yes.
Okay.
Yes. It's the number of cases.
Okay, I see. So the disease is not dying out. It's still going on. Okay.
Yes.
Thank you.
Yeah, thank you.
Do we have any other question?
Yes. Can I ask my question?
All right.
Okay, can you hear me?
Yeah.
Okay, thank you. So for the case of Burkina Faso, we tried also to model COVID-19, but we faces a major problem.
Okay.
The problem is that the number of cases used to increase with the number of tests which are being done. So when COVID-19 started, we were not having enough tests for the entire population or for all the people who were suffering from COVID. So it depends on the number of tested of people we used to test per day. We can see when we test more people, we will have more positive. When we test less, we will have less positive. So finally, all our predictions, our model finally did not work out because it was so clear. It was a clear cut. You can see when the number of tests increase, the number of cases increase, and so on. So I wanted to see if this was also a problem we encountered during this study. And because in this case, all your trend you are saying here is just a matter of the tests which have been done, right? So I don't know if you were facing the same kind of similar problems during this study.
Yes, I think I just look at this for the purpose of this presentation or this talk. just narrow the presentation to just Nigeria, but we have a case because we consider the whole African country, the 56 African countries, yeah, and we have such kind of a situation in some of the trends. Well, some of the trends are working fine. In fact, that is why in the future publication or in the future work we are doing, we have an additional models which even show, not even quadratic or linear. We have some models that give a completely different trend, and I'm sure that this is why one of the reasons you mentioned now. This is one of the reason in some of the countries. So we don't have the actual, the number of tests as you said. So it really affected the data. It's not only to Burkina Faso, it affects other countries in Africa.
Yeah, but let me make a comment there. I believe that the model can be conditioned on the number of tests. So that testing will be a condition or one of the conditions that will be taken into account. Because one can still model and predict, but based on the testing condition or the testing feature, that could make the model much more viable.
Exactly. It's okay. Thank you very much for this also contribution. We'll look over that. Someone is raising hand. Yeah.
Okay, who's that? Okay, Gaston. Okay,
yeah,
Gaston, please.
Good day, everyone.
Good day, Gaston.
Thank you very much for the presentation. Mine is just a comment. It would be interesting to see what sort of results you'd get if you use quantile regression. Compare it with the approach that you've used for extreme value theory. Compare it with the quantile regression approach.
Okay.
Thank you. Yeah, that's all.
Especially for the prediction purpose, right?
Even for estimating those quantiles, extreme quantiles.
Okay, for the estimation purpose and also for the for the performance measure. So the quantile regression will also be an additional option, right? So that we can see possible maybe what will be the difference, or when compare we can see the difference, right?
Yeah, that is the idea. Yes, you can use it to estimate extreme quantiles.
Yeah.
Or you can use it to predict the median. Instead of the mean, you can predict the median values.
Yes.
But in this case, you are interested in is it the quantiles, 2.5 percentile, 5 percentile, and so on.
Yes.
So quantile regression can also be used in this case.
Yes.
So my comment is, if you do a comparative analysis of the two, it would be good.
Yes.
Because normally with extreme value theory, the way it was developed is based on an asymptotic theory.
Yes.
But its development initially was based on the idea that we are looking at rare events. Rare events. So rare events, these are events which do not occur every time, but at the end of the day, when they do occur, they're catastrophic.
Yes, correct.
Yeah. So if you could perhaps compare the extreme value theory approach with the quantile regression approach, it would be really interesting to see what sort of results you will get.
Exactly.
Yeah. So it's a comment, it's not a question.
No. It's important. It's a very important comment, and we'll look over it. We will look over it to make an improve to see the improvement, because doing that will also give us the insight or on the competency, on the quality of the extreme value theory concepts. So thank you very much for this suggestion, and we'll look over it.
Thank you.
We have another one raising hand, Dr. Jeprik.
Yeah, thank you, Chairman, and thank you, the presenter, for a nice presentation. One part of my concern has been addressed by the speaker the one who just finished speaking. The second part of it is, I'm looking at the title. It's talking about new cases, but we do know that COVID is no longer in session. So when you talk of new cases, unless maybe in the main work, there's a session where you define the scope, where you explicitly define what each of these terms mean. It may seem to appear as though we are having those cases now. So I thought that looking at it from the viewpoint of daily infections may well have been more appropriate in this era than where it is now. Then in the case of the abstract, I realized that there were some paragraphs. An abstract naturally should always just be one
one paragraph. Yes, correct.
One paragraph.
Thank you.
So if in the main work itself is like that, you may want to look at it and then work on it.
Yes, it's
Otherwise,
okay. Yes.
thank you for a nice work, John. Done.
Yes, thank you very much. Please, but I have something to add just to your case. Though we look at the COVID-19 as cases that is over, but in reality it's not over, because from this side, the link we have there, we are still having cases of COVID-19 on daily basis. Even as of yesterday, you can still have some record on so many, on almost everywhere. So from the link, they have a record of daily cases up to date. So, and this record we have, I think it's up to August, towards end of August. So I am very sure that even today or yesterday, you will have found the case. So it's just real. And now the public are not much interested in knowing much about it, but we still have the cases of COVID-19 around the world, but it's at its minimal level. Thank you very much.
Okay, your point just brought me to the fact. Okay, your speaker was supposed to speak. The Mark Johnson from MIT. I think he just emailed me and said he had COVID as well. So,
sure.
So he has been on school. He has had COVID for the past 1 or 2 weeks. So,
oh, sorry about that. We're really sorry. So it's okay. So I think, Dr. Kunsley, we can move on to the next agenda, right?
Yeah, I think we can.
And the next agenda is our presenter, Dr. Edson, right? We don't know if
that's right.
If Dr. Edson is there to give us his insightful and encouraging talk, which will be the closing ceremony of today.
Okay. Thank you so much to the moderator, and thanks to the organizer, Dr. Sarah Lees, for inviting me to participate in this workshop. So you have known Dr. Sarah Lees for a long time now, since 2010, when I first arrived in Manchester to study for my PhD at University of Manchester, where he is based. And then I later moved on to Lancaster University to complete my PhD. But he supervised another colleague of mine from the same university in Nigeria, who is now based in Saudi Arabia. So we've known each other for quite some time now. So I just want to kind of give a bit of my background, share a bit of my background, and then maybe share my experience working with professional statisticians, as part of my research. Yeah, so I did my PhD in spatial and spatiotemporal statistics, looking at novel methods for addressing the problems that arise from data collected over space and time. So when I finished my PhD, I returned to Nigeria, spent some time before coming back to the UK to start my postdoctoral fellowship and I've been in the UK since that time. So I came to Southampton, where I'm based now, to start my postdoctoral fellowship, and I've worked on a number of projects at Southampton. So by the way, I belong to a research group at Southampton called WorldPop. So WorldPop is a research program that focuses primarily on producing graded population estimates. These are produced annually for all countries of the world. And we also map various population characteristics, migration, reproductive, maternal, child health indicators, and all sorts. So since joining University of Southampton, I've worked on various projects, and somehow I started focusing mostly on spatial and spatiotemporal methods, for producing estimates of child health indicators, particularly in low and middle income countries. And more recently, I started focusing on producing graded estimates of childhood vaccination coverage. And the rationale behind, this area of work is that, when surveys are implemented to collect data that are used to produce estimates of these indicators, the surveys are usually designed to be representative at the national level, and maybe at the regional level, regional or provincial level. And these are usually admin level 1 areas within countries. So, but oftentimes policymakers require estimates at lower admin levels, for example, at the district level, or even at the ward level, and there are global targets, that are set at these spatially resolved skills, if you like. So, but then when surveys are implemented, because of the cost of collecting a lot of data to be able to produce estimates at these resolved spatial skills, so usually most surveys do not produce estimates at those skills. And so when we're able to get geolocated data from these surveys, so when the survey is being implemented, the interviewers, they record the GPS coordinates of the locations that they visit. So when we have that information, we can integrate that with what we call geospatial covariate information. We do some modeling, and that enables us to produce estimates, first of all, at the grid level, which is not subject to any boundary constraints. And then we can aggregate the estimates that we produce at the grid level to any administrative level, to the ward level, to the district level, and so on. And so there are other things that I have done that are related to what I just described. But over the years, we've received funding from various organizations for the work that we do. We've received funding from the Bill and Melinda Gates Foundation. We've received funding from Gavi, the Vaccine Alliance. We've received funding from WHO, from UNICEF, and a number of other organizations. And so we don't just sit here in Southampton and do this work and have it published in a journal, whatever. So one of the things that drives the research that we do, is this desire to generate some impact, to have the output that we produce get utilized for policy and decision-making in different contexts, within various countries. And so also recently, I've been doing some work in Nigeria focused on coverage estimation and analyzing surveillance data to sort of produce evidence that is used for targeting at-risk or zero-dose populations within the country. And so in Nigeria, we've been working directly with colleagues from the Ministry of Health, in particular the National Primary Healthcare Development Agency, NPHCDA. We work with colleagues from the National Bureau of Statistics, work with colleagues from the National Population Commission as well. Don't know if I'm leaving out any other one. And so there are professional statisticians in these organizations that we work with, and over the years we've built some relationships with them. Okay, so yeah, so it's been the case that maybe we have a funder, okay, identify a problem within the country, right? And then they know that we have the expertise to develop a solution to address this problem. So they approach us and give us some funding to develop the solution to address the problem. And then in the process of doing that, we often have to collaborate with in-country colleagues, mostly from various government agencies, and we often kind of co-develop the solutions with them, or is the case that maybe they were responsible for collecting the data that we needed for the work, and so we would liaise with them to obtain more insights, about the best way to go about analyzing the data. And then we've also had instances where we sort of co-developed grant proposals, and then we approached a funder to give us funding to work collaboratively with them on the project in question. And so yeah, this has been my experience in brief, and I think that one way to approach this sort of conversation, is for people to kind of share their experiences working with professional statisticians, whether those are statisticians in industry or in the government sector. And if anybody has had any experience regarding maybe whatever assistance that they received from a professional statistician in these sectors to help with their research, yeah, I think it'd be good to sort of hear from them as well. Yeah, and maybe I'll bring up a number of other issues later on. Yeah, but by the way, do we have professional statisticians in industry or in the government sector on the call, or are we all academic statisticians?
I think we have one or two, a few from the Bureau of Statistics. I think maybe. Okay,
from which country?
I think there's one from Uganda.
Okay, that's good. Yeah, because I think that to keep the perspectives balanced, we need to hear from academic statisticians and professional statisticians as well. So yeah, I think one thing that is important in encouraging collaborations or partnerships, between professional statisticians and academic statisticians is networking. So are there like platforms where both groups of statisticians kind of get to meet and interact, discuss interesting problems to work on together? So it'd be good to hear if there are such platforms in different countries.
I have a question for you.
Yes. Okay, yes, please go ahead. Yeah.
This you mentioned something on impact pathway.
Yeah.
Yeah, because I think now a lot of funders not only looking at maybe publication pathway, but a lot of funders are looking at impact pathway. What's your take on, or you that have experienced quite a number of that, the difference or the level of acceptance with those who have impact and those who have a lot of publications with when it comes to funding? What's your take or what's your experience on that?
Yeah. Okay. Yeah. Thank you very much. Yeah. Yeah. Usually, as we say, it's, you stand on the shoulders of those that have gone ahead of you. I think so far in my career, I've been lucky to be mentored by those who have done some really impactful research, mostly applied researchers rather, working in global health. So, and, because I started off working, with them, so I would say it's kind of quite easy, for me to collaborate with them on projects, get their inputs on the project I'm working on, or collaborate on grant applications. So if I've identified a particular grant call that I think I want to apply to, so I can approach them, ask for them to collaborate with me on the application. So, and yeah, my experience has been smooth so far. So I think maybe because I've been lucky to work with to be working with very nice people. So, and then on the other side, so because sometimes when certain grant calls are made, they require you to get like a statement of support, maybe from an implementation partner. Okay, for example, I do a lot of research focused on improving child health in LMIC settings. So if I'm applying to develop a new method for estimating childhood vaccination coverage, for example, a funder may want to know whether the outputs of the research that I produce, will actually get utilized anywhere. And so they would want me to collaborate with maybe government partners on the grant application. So, and I would say that, yeah, so the people on the policy side, they know the problems that they face, right? And so if the problem that I'm proposing to address, if it aligns with what they've identified, to be a major challenge in the country, chances are that they would want to collaborate on that grant proposal. So, and so far, the few times that we've had to approach in-country colleagues, to collaborate on research grants, we haven't had any major challenges. And one of the reasons behind that is that we've built a relationship with them over the years, and some of those relationships were initiated by the funders. And as I mentioned earlier, so the funders will kind of approach us, ask us to work with them on a certain project, and then they would link us up with in-country colleagues, who are usually the ones that implement the outcome of the research that we do. And so that way, yeah, so we've been having a smooth working relationship, if I put it that way. Yeah, so yeah, gaining acceptance, yeah, hasn't been a major challenge that way. Yeah. I don't know if other people have other experiences, maybe that are different to mine.
Well, I have something to say, Doctor.
Yes.
Well, it's very obvious, and we can say that you are one of the luckiest people, in statistics to have such opportunity, because it's very rare that, And it's very clear that having the grant maybe on an applied area, it's more successful compared to the, the abstract areas. Because all you mentioned now, for those grants that were successful, you realize that they are on based on maybe on health issue, on populations, on all these kind of things. So in statistics, we have a very important and significant role to play in all these aspects. But is the gap? How can we have such collaboration with those people that are related, that are into health, that has such higher chance of getting the grant? And secondly, is all those grants that were successful, are they related to African research, or most of them are related to the UK or the foreign countries? Thank you.
Okay, yeah, that's a very good question. So I'll start with the last one. Yeah, as I said earlier, I work mostly in LMIC settings, which means that I use data from mostly low and middle income countries for my research. So my research is pretty much focused on Africa and some countries in Asia. Yeah, just to answer that first question. And then, so how do you build, relationships with these key people, whether professional statisticians in the private sector or in the public sector, to help sort of enhance the research that you do? So I think that there are certain platforms, that can encourage networking among different groups of statisticians. In Nigeria, for example, there is the Nigerian Statistical Association. I know that the membership comprises statisticians in the government, in the private sector, and academic statisticians. So, and when they hold their conferences, that's really an opportunity, for these different groups of statisticians to come together, share their work, get to interact with each other, get to network. And so I think that's one way of building this relationship. So the other thing is, so if there's a particular area of work where you are seeking collaboration, it would be good if you can demonstrate that you have some experience or you have done some work, in that area. Because if you go to a conference and, okay, let's say you want to collaborate with people from MPA CDA, and you haven't done any health-related research, then it will be quite difficult, or it will be challenging, to get their attention or to convince them, to collaborate with you. So once you've identified an area that you are interested in, which is actually one of the things that make us well-rounded, statisticians, you have the knowledge, you have an area of application, you're good in computing, and so on. So once you've identified that area, so try to develop, your skill set in that area, and try to maybe identify topical issues in that area that you can work on, even if maybe you've not developed a full methodology yet, but sort of doing some preliminary analysis, with some interesting data addressing a very important problem, can actually attract the attention of the people, who are supposed to maybe utilize the findings, from that kind of research for their everyday work. So, and that way you're able to attract their attention or their interest. And then the other way as well that I've talked about earlier is, if a funder is interested in you, they know that you're able to, you have the capacity to deliver, they can actually initiate that linkage with the implementers of the outputs of the research that you produce. So I think it requires deliberate planning, deliberate efforts to get to this stage. And of course, you need mentoring as well. You need people that have already establish this kind of networks, to bring you on board as well. Yeah.
There's someone.
Hello, Edson.
Yeah, you can talk.
Yes, okay. I wanted to use this opportunity also to share a bit of my experience as well, if it is possible, quickly. Of course, I did not present fully myself. I am working at the Institute of Research in Health Science in Burkina Faso. So this institute is the governmental body of research in health science. So we are highly related to the Ministry of Health. 90% of our finance are coming from grants. So most of our work is applying for a grant and implementing the grant. So that's what we do all the time. So, but we are highly related to the Ministry of Health, as I said, and most of us, we have PhDs, and we are also lecturing at part-time at the University of Ouagadougou. So most of what you are saying is exactly also what we are doing, working with the Institute of Statistics in the country, working with other departments of the Ministry of Health, trying to figure out some problems, and most of the time applying for Bill and Melinda Gates Wellcome Trust fundings. Sometimes the fundings are not in our, is not like we prepare ahead topics. Sometimes when they open funding, they have like the topics they want people to apply based on the topics. So we'll see the topic going in our area of health, and especially in maternal health and things like that, reproductive health. So I just wanted to mention that as well. All right. Okay. Thank you.
Thank
you very much. That's quite insightful. Yeah, it's good to know that. Yeah, there are people who've had similar experiences. Yeah. So, does another person have any other contribution?
Yeah, sorry, Doctor, as the last speaker just mentioned on the Burkina Faso case, which how they related to with the Ministry of Health. Also in Nigeria, as you made mention of the National Bureau of Statistics and some few ones among them. And I'm surprised sometimes you realize that almost most of them, they have the statistical units, they all have their statistical, because even in the health, no any survey will be conducted or no any research, whether survey that will be conducted without statisticians, because from the survey, from the beginning of the survey to the middle to the end, up to the data, the analysis part, statisticians play a vital role. But unfortunately, sometimes you realize that all these grants will come in, but whatever you try, whenever you attempted to make an application, you realize that it's unsuccessful. What do you think cause all this kind of delay and challenges, and how can we overcome them? The question is to you and also to the other person from the Burkina Faso, so you can share light. Maybe if we can apply the concept you apply here to win or to draw the attention of the ministry of other country on the way to have a collaborative between this academician, especially the statisticians, with those ministries in conducting survey and in doing some research, in having funding for some specific, area of interest.
Yeah, that's a good question. Yeah, you were right to say that, okay, if you take the National Bureau of Statistics in Nigeria, for example, so that is one of the biggest pools of statisticians in Nigeria that I know. So they have a lot of statisticians in their workforce, and so one of the things that they do is that they design and implement surveys, on behalf of the Nigerian government. So they have a lot of survey experts. Yeah, so and usually, these survey statisticians, because they work in the field, so they understand all the practical challenges in the work that they do. And so I think it is quite important if maybe academic researchers, have good linkages, with them, so that, you're not just working on problems that kind of end up in journals. You are working on problems that actually have some importance, in the real world, that can make an impact. So they usually know, what the challenges are. And I think that, in the area of problem identification, if academic researchers have close collaborations with them, it'll be quite easy for you to kind of identify real world problems to work on. And of course, if you collaborate with them, you'll be able to demonstrate that whatever work you're proposing to do, will likely make some impact. So I think these are some things, that need to be included in a grant application, to make it successful. So of course there are other elements, that I haven't touched on, but sort of being able to demonstrate the impact or the significance of the research, I think is very important. Yeah.
Okay. Thank you very
I
much.
want to add.
For this. Okay. And before you add,
Yeah.
please, before you add, you and Edson, it will be good, though we will continue with the discussion, because the collaboration just started, because we would like to have maybe some of the samples, some of the grant application you have done that are successful, that maybe we can look forward and how to make an input, and at the same time find other alternative or other place, or try other places as well. Thank you very much. Maybe you can talk maybe in brief, because we are running out of time.
Yeah, I will be very brief. I just want to say, in the case of Burkina Faso, the main problem we have with our colleagues at the university, when you are applying for grants, there is this budgeting problems. At the university, their finance system is quite very rigid. So when they have grant, even to implement the grant, they have a lot of issues with their finances. But at the research institution, we are more flexible in how we run the grant and how we allocate fundings, and it is easy to apply the money. So this is one of the very big problems. But most of our fundings, we always include the university. It is not easy to have a grant without working only in research institution. Usually we have partners at the university, but only that the money is in our institution. That's what we usually do. That was a quick addition.
Okay.
Thanks.
Thank you very much. Thank you, Edson.
That was quite an eye-opener.
Yeah. It's interesting. The time was against us, Dr. Quinsley, but we don't even want to go, because the section is quite interesting. This is where we want to have more information. So maybe with time, we'll have a time that maybe 1 hour that people are it's comfortable with people and discuss a lot on these issues.
Yeah. I do agree with that.
Yes.
Yeah, thank you so much. Just to wrap up on my own side.
Okay.
So what has worked over the years for me, so the professional statisticians that I've collaborated with, so they are either data providers, okay, so they collect the data that's I use for my work, and so when I request the data, we kind of establish some collaboration. So we ask them to be co-authors on our paper, or we kind of co-develop a methodology with them. So either they are data providers, or they are actually the people that are on the implementation side, helping policymakers, interpret data and turn them into actionable insights. So, I think the people that are on the policy side, they tend to be more in tune, with the latest challenges in the area of research and so on. And so, oftentimes we're having to work collaboratively with them, to address those challenges. So I think, these are valid ways, to sort of have collaborations with professional statisticians, and get them to facilitate, the research that those of us in academia do. And yeah, I think you probably work for other people depending on the research area that you are working on. Yeah. So thank you very much. Thanks for
thank you very much, Doctor. Thank you. We really appreciate your time and insightful information, and based on the experience we have, we truly appreciate, and we look forward to continuing working and collaborate together now and in future, especially in helping in improving our research activities, in improving our personal developments based on research, and also assisting brothers and other colleagues in the African in order to improve their statistical knowledge, and at the end for assisting even the government and policy makers to make some implementation towards improving the standards, both economically and all other activity in the African countries, so we can compete with the international world at any time or in future. This is our wish. Thank you very much. Thank you everyone for attending and your contribution. And we see you tomorrow for the last day of the workshop. I think tomorrow time, I don't know, Dr. Quinsley, when are we starting tomorrow?
Say 11:45 GMT.
Okay.
British time. 11:45 GMT.
Okay.
British time. Yeah.
So it's okay to thank you very much, and
all right.
have a nice day. See you tomorrow. Thank you.
Yeah. Take care.
Everyone. Bye.
Bye. Thank you. Bye.
Bye.
Bye-bye.
Thank you. Bye.
Yeah, bye. Thank you. Yeah, thank you very much. Thank you all. It's not easy. Thank you. Yeah, thank you all.